So hello and welcome to this Prism Sound webinar, the latest in our series of educational test and measurement webinars. Today we're going to be taking a look at Bluetooth audio headset testing, and we will be looking at both the electronic analysis and the acoustic analysis of a typical Bluetooth audio headset or headphone system. Now, I'm going to be using a combination of PowerPoint slides and real live measurements on a test setup that I have on my bench here. So we'll be swapping and changing between those two different formats as we progress through the webinar. Before we get really started into looking at the theory and background and some practical demonstrations of measurements, what I want to do is just involve you briefly and find out one or two pieces of information from you. Now, without really explaining too much about what I'm doing here, I'm going to switch over into my audio test and measurement system that I'll be using for my demonstrations here today. And what I'm going to do is I'm going to assign a Bluetooth audio dongle as my output device from my test system. So this here, the CSR audio adapter, is a Bluetooth transmitter, a Bluetooth dongle. And I'm going to assign that as an output device from my test system. I'm measuring the output of the receiving end of the Bluetooth system, and I'm currently showing you the live waveform of the output from that device. Now, if I tell you that this is a 1 kHz sine wave that I'm generating, and if I just zoom in a little here, you can see the waveform on your screens right now. And in fact, if I turn up the monitor outputs on my test instrument, we can actually listen to that waveform as well. That may sound slightly distorted down the telephone transmission lines, but hopefully you would have heard that, and you can also see that trace. So what I want to ask you, without really explaining anything further, is if you could just tell me whether you think that that particular signal looks and sounds okay. Now, using your ears will be difficult down the telephone, but just take a look at the sine wave and see what you think. I'm actually publishing a survey now, so you should have a message box popped up on your screen unless you are a Mac user, and that message box will allow you to answer the question about the waveform and then just to give us some further feedback as to your level of experience in the field of audio test and measurement. There is a question there with a multiple choice series of answers telling us a little bit about the kind of systems that you may have used for audio analysis in the past. That survey is just running. I'm going to let that go for a couple more seconds, so if you do want to answer the question, then please do so in the next couple of seconds. I'm going to stop that in 5, 4, 3, 2, 1. Okay, I've stopped the survey, and let's just take a quick look at the results. And you can now see that on your screens, and we can see that about 50% of you answered the question. Perhaps I didn't give you long enough there, for which I do apologise. We seem to have a majority consensus that the waveform looks okay, and some of you think that the waveform perhaps doesn't look okay. Keep this in memory, because we will return to this very shortly, and we'll take a look at what may or may not be wrong with the signal that I'm currently analysing over my Bluetooth radio interface. Looking at the second question, there is a good mix there. A few of you have used Prism Sound audio test instruments in the past. It's good to see we have some existing customers who've come to the webinar, but we also have some people who perhaps haven't used our systems. They've used other manufacturers' systems, or perhaps different types of audio analysis instrumentation there. So that's good. There hopefully should be something for everybody in this session today, whether you're a Prism Sound test instrument user or not. So we shall close the survey for now, and I'm going to go back into my slideshow just to set the scene for the rest of today's session. So as I say, we're going to be taking a look at the kind of measurements you might want to make both electronically and acoustically, and we'll be using a single test instrument, our D-Scope Series 3 platform, which I will describe in a little bit more detail later, to make those measurements. So before we start, let's just have a look at what a typical Bluetooth headset system may comprise. And this first example is something with which I'm sure the vast majority, if not all of you, will be familiar with. And this is a telephony handset, something like a mobile telephone, and a Bluetooth audio headset, which is a bi-directional audio device carrying the send and the receive signal paths from microphone and transducer to and from the phone. Now, typically a telephone and headset system will be operating using what's known as the Bluetooth hands-free profile. This is a particular profile that is designed to carry voice band audio in two directions in mono. There are many other types of potential Bluetooth audio systems, and one of those may be a Bluetooth stereo headphone that's designed for music listening purposes. And this typically comprises a USB dongle that connects to your host PC and allows you to stream audio from perhaps your media player or your internet browser to a pair of headphones over the Bluetooth interface without wires. And this system, as I say, comprises typically a dongle and a headphone or headset, and typically uses what's known as the A2DP or Advanced Audio Distribution Profile in order to transact the audio data. Now, this is a monodirectional transmission from the Bluetooth dongle to the headset. There is no microphone channel in this particular example. Let's now look under the hood of this system in a bit more detail, and I'll describe to you the system that I have on my bench today for test purposes. So I'm going to use an example where I'm going to actually deliver audio to my either headset or headphone using a USB dongle as my Bluetooth transmitter. Actually, the device that I have on my bench is a development board from a company called Cambridge Silicon Radio, or CSR. And CSR supply, I think it's fair to say, the majority of all of the Bluetooth audio chipsets in the telephones and other devices that have made it into commercial production. So this board is set up on my desk as a USB source for my Bluetooth transmission tests. And I have a second board, an identical 1645 evaluation board that has been configured with a different profile, and it is set up either in the hands-free profile, i.e. the bidirectional communications profile, or alternatively it can be configured in the A2DP profile mode for carrying high bandwidth stereo audio. Now, there are other Bluetooth profiles that these boards can be configured to support, but these are the examples that I'll be talking about today. Just to clarify, the Bluetooth chipset is actually a very small component within the development board, and of course it needs to be in order to fit into this typical headset device that we see in the diagram or the photo at the top of the page. What I'm going to do now is just explain to you the majority of the components and subsystems that appear within the Bluetooth audio system, and I'm just going to describe a schematic to you so you have an understanding of the components and systems within our evaluation board that we're going to perform analysis upon. So, as I've described to you, at one end of my system I have a USB dongle attached to my host PC, and at the other end I have a second board which is designed to act as a headset or headphone. So let's take a look at what that actually encompasses. Well, we will have some external components, a microphone and or some headphones or a earpiece. And then within the electronic functionality of the board itself, we have obviously a Bluetooth transceiver in order to communicate with the dongle over the radio interface. We'll also be employing some kind of codec. Now, the codec that I will be using today is known as SBC, or sub-band codec, and that is an algorithm, a codec for compressing and unpacking digital audio data so that we can use a smaller transmission bandwidth than we would otherwise need to transmit uncompressed pulse code modulation, or PCM, digital audio. Now, Bluetooth as a technology can support a number of potential codecs. The reason I'm using sub-band codec is that it is a mandatory codec that all Bluetooth audio devices need to support. There are other possible codecs that manufacturers may choose to implement on their designs, including AAC, or Advanced Audio Coding, aptX from APT, that's another alternative high-quality audio codec, and Bluetooth is also potentially capable of transmitting lossless pulse code modulation, PCM, digital audio. After the codec, we typically have some form of digital interface to move digital audio around the board between various different areas of processing functionality. And I've illustrated that with the abbreviation I2S, which is the abbreviation for inter-IC sound, which is a common or commonly used format for routing digital audio between devices at board level. In the microphone direction, we would need to have a preamplifier, and the preamplifier is followed by an A to D conversion process to convert our analog microphone signal to digital audio. We will then have potentially some signal processing, which may be dynamics or EQ or potentially other more sophisticated processes. And in the headphone direction, we have a similar setup whereby we have some signal processing, a D2A converter, and a power amplifier to drive our earpiece or our stereo earphones. So having looked at the system that we will be analysing today, let's just take a quick overview of the various modes of functionality that we're going to test and analyse today. Now, first of all, I'm going to look at the Bluetooth link itself, and one of the first things that you might want to do as somebody who is designing or verifying a Bluetooth audio system is to verify that the Bluetooth communication, the wireless communication between the source and the receiver is up to spec. In other words, that you meet the anticipated range, which may be typically anything from a few meters to a few tens of meters, depending on a number of parameters. And if you exceed the range that the system is capable of, then you can expect to start to see dropouts. And you may also see dropouts if you're in the presence of a large amount of background radio frequency interference. I'm then going to move on to take a look at some converter measurements, and I've chosen D2A conversion for today's example, and that will allow us to take a look at serial digital interfaces at the same time. I'll give you an example of some signal processing analysis, and I will be choosing to make an EQ measurement today. We'll then take a look at analysing the power amplifiers, and then finally we'll move on to some electroacoustic analysis where we'll look at making some measurements on the acoustic components within the system. So part one, the Bluetooth link. Let's get straight into this now. Just to explain what I have set up on my bench here today, I am using the D-Scope Series 3 audio instrumentation interface, and this is actually a family of hardware interfaces according to your specific needs, but in broad terms it can support both analog and digital audio generation and analysis. So this is the hardware interface, and it connects via USB to my PC. It's actually running on the same laptop that I am using for this PowerPoint slideshow. So that is the test system, and the software will allow us, when we switch over, to actually illustrate the signals that are being generated and ultimately analysed, so you can actually see them as I make the measurements. To my host PC, I also have connected the first of my two CSR development boards, the 1645 development boards. And as I explained earlier, the first of these two is acting as a USB dongle, so it is simply connected via USB to my computer. It will be transacting data with the second of my two boards using the Bluetooth radio link, and in this first example this board is configured to support the A2DP profile, and if you recall, that is the wideband profile designed for carrying stereo music signals. So I'll be taking the stereo outputs from the headphone jack on this board, and I'll be analysing them at the analog inputs to the D-Scope system. This will hopefully make more sense if it might be confusing already if I show you a photo, and this is actually the test setup on my bench. Now, there are a number of components in this test setup, and these will be used at various stages during the presentation, so I'm just going to highlight exactly what I'm using for this first measurement. And here is the D-Scope hardware highlighted in red here. My computer is out of the picture, just in case there's any ambiguity there. And these are my two Bluetooth boards, and of course they're very close to one another on my bench right now, and in reality they were probably used at a greater separation than that, but it allows me to illustrate the concepts nonetheless. What I'm going to do is show you a really useful way of checking for audio dropouts, and as I've said, that can be an indication that we're on the edge of the limits of either the range of the product or its tolerance to background noise. background noise in the sense of radio frequency noise. We've got some really powerful tools in the Dscope software that we call the Event Manager and the Event Log file that allow us to test for a very wide range of intermittent faults, which may or may not include things like glitches caused by audio dropouts, packet loss. And that's what we're going to set up as a test today. So I have just switched over to my Dscope Series 3 software, and you will now see the same screen that we took a quick look at earlier on. So just to confirm here, actually I'm not going to show you my generator function, I'll come back to that. It is a 1 kHz sine wave. We can see the result of that on the screen here in front of me, and if I turn the volume up once again, just to clarify what I'm doing there, that is the monitor outputs from my instrumentation hardware. I have a volume control on the front of my Dscope, and there is a loudspeaker on the side and also a headphone jack, so I can actually listen to signals and residual signals to verify that I'm receiving what I expect to see and hear. So I asked you the question, does it look like there is anything particularly wrong with this audio signal, or does it sound like there's anything wrong? And the majority of you would be inclined to agree with me that there really doesn't look to be a great deal wrong with that signal. In fact, let's just zoom out all the way. We have quite a long duration. We've got over 600 milliseconds of audio here, and we appear to have continuous audio, no apparent signs of any glitches or dropouts here. So let's just switch over to a different page here within my Dscope configuration file. And you can see that there is some activity here. At the top left-hand side of the screen, I've got a couple of analysis results. And these are periodically flashing red. And when they flash red, we see that there is data being written into this event log file. So what am I actually observing here? Well, if I go to the continuous time detector, which is one of the analysis instruments within the Dscope software, and that is what these reading panels at the top left here are showing us. I'm actually measuring THD plus N, total harmonic distortion plus noise. So that is everything apart from the 1 kHz signal that we should be seeing. And if this transmission path is completely free from dropouts and glitches, we should see a fairly constant, or in fact a very constant reading of THD plus noise. But as we can see, we're getting some occasional errors here in the reading. It's breaching the limits that I've configured and flagging a problem. One important thing here to mention is that I'm analysing in peak mode rather than RMS, and it's very important to have a continuous time instrument that can read peak THD plus N if you want to pick up very potentially short duration glitches that would otherwise be possibly lost in an RMS reading. You can see here that I'm reading amplitude in RMS units, and these readings are absolutely fine. They look to be perfectly static, and that's because we are integrating over a time base. It's actually set up to auto at the moment, but any potential glitches, any relatively short duration glitches, will not necessarily be picked up in a RMS reading, and that's why it's so important that we can use a peak measurement here. I haven't really illustrated what's going on here, but what I have done is I've actually configured a special kind of waveform. I've loaded a user waveform, which can be anything. It's totally arbitrary, and I've loaded a wave file. This wave file I have configured deliberately to have one single sample of data in error. I've actually manually moved one sample of data in a digital audio editing package in order to produce a very, very small glitch. And if I now go to my time domain waveform here, what I'm going to do is add a couple of traces and then explain something to you. So let's just I'm turning on the FFT trace now. This is the fast Fourier transform trace, and this shows us the spectrum of the incoming signal. Now I'm actually implementing a notch filter. This is the 1 kHz notch filter that is being applied in the continuous time detector measurement, showing us the residual THD plus N with its peak analysis mode, peak response. And I can actually look at the output of that filter too. So this trace here, the light blue trace, is the output from that THD plus noise notch filter. So let's just turn on some additional traces, and let's zoom all the way out. Now, immediately we see that there's a potential issue there. The continuous time analyzer output, the output from our THD plus noise filter, shows a large peak at this point here in the trace window that I'm just looking at now. And that has breached the limits that I have previously configured, which was what was leading to the results here in red flashing a warning at me. And of course the error being written into a log file. And if we zoom in on this area here, then hopefully we can see the reason for this glitch. So I'm just going to keep on zooming in here, and as we get closer and closer we should start to see right here, there it is. If we look at the live scope trace, there is the one sample of glitch that I've deliberately engineered and loaded this as my waveform. So we can see here that this is a very powerful technique for picking up potentially very small or very short duration glitches that we might expect to see in a system that may be starting to experience some loss of data. Now, ordinarily in a Bluetooth transmission, the amount of data that will be corrupted if we'd dropped a packet or repeated a packet because we didn't have a new one to play out, our glitch would be significantly larger than this. But really what I wanted to show you was that we can pick up even very tiny glitches, so that this is a totally robust way of being able to pick up those kind of problems. So having illustrated this analysis methodology to you for picking up potential dropouts and glitches and other kind of intermittent problems, I want to go back to my slideshow now and just talk to you about the next area of discussion here. So I explained earlier that we were going to take a look at a D2A converter measurement. Now, there are many things that we could talk about in terms of measuring converters, whether they're A to D or D to A. And in fact, all of these topics we'll discuss today are topics that would warrant a webinar in their own right. We're really just going to be scratching the surface, but we will be coming back to some of these issues in a more general sense in future webinars. And indeed, we have covered things like power amplifier analysis in detail in the past. And we do have a download page on our website where you can actually download previous webinar content. So just to conclude on that, we're going to look at a couple of measurements on a D to A converter and then move on. So to explain my test system here, I have my D-Scope hardware and software running once again. I have a single 1645 board this time, and what I'm going to do is introduce a second member of the D-Scope test instrument family, and this is a peripheral device that is supplied separately to the D-Scope hardware if you need it. Now, this is what we call our VSIO adapter, and it's an interface converter that exchanges data between the D-Scope's native AES EBU digital audio format and serial digital audio formats such as I2S and other serial data formats that are used at board level. The reason for introducing this component is that I want to test just the converter and nothing else in this system. So in other words, if I were injecting my signal via Bluetooth, as in the previous example, I would be measuring the codec and potentially a number of other components upstream of the D2A converter. And actually, really what I want to do here is just measure the converter and nothing else. This VSIO adapter is a bidirectional device, so it will convert to and from serial digital formats, allowing us to generate and analyse serial digital data. But for today's session, I'm just going to look at a D2A measurement, and therefore we'll just be using the generate direction. I'll then take the analog output from the headphone jack on my development board once again, and I should have shown that as a stereo measurement. Please forgive me that little indiscretion, but we'll be looking at two channels of output from the 1645 board here. So, my test setup for this measurement. Once again, I'm using the D-Scope hardware, and here is the VSIO adapter, the grey instrument at the bottom of this stack of equipment here. Now, actually, to make this easier for me to set up and to make it smoother during the process of running through this webinar, I'm actually going to use an external D2A converter. And the reason for doing that is that means that I don't have to switch profiles on my CSR development boards, and I can just very quickly switch over to this measurement. But the logic applies nonetheless. We're going to be setting up a D2A measurement which is generic, and that it's equally applicable to any board, not just this development board from this manufacturer. So let's go over to my Dscope software, and for those of you not familiar with the Dscope operating environment, we have a series of pages available to us. We've got 5 pages here down at the bottom of the screen, and on any page I can set up, for example, my signal generator. I might want to simplify that. I can open the signal analyzer, I can pull out results. The idea here is we can set up a test configuration that we return to at a later date, and we can perform a save as operation and then browse to whatever test file we want to open. But for convenience, I have configured this user bar at the top of the screen here with a number of tests that I want to run through today. So I can very quickly and easily just click this button here, and this will take me straight to the next test that I want to illustrate to you. I've got a little note to self here. This yellow memo here is telling me I need to adjust my connections if I want to make a successful measurement here. So I'm just connecting the D2A converter to the Dscope hardware as we speak, and having done that, I can now get rid of that little note there. Right, as I said, I'm not going to dwell on I2S in too much detail. We'll cover this in a future webinar, but in essence, what we have here on the left-hand side of the screen is the control interface for the VSIO adapter, the interface converter that we just took a look at. And this allows us to set up the clock and data formats in whatever way we need in order to comply with the manufacturer's specification for whatever part we are analysing. And down at the bottom left, or bottom right, sorry, of my screen here, you can see that I have copied and pasted some data from the manufacturer's datasheet into this Dscope configuration file. So this tells me exactly how I need to set up the various serial clocks and also the data. So very briefly, let's look at the data. Well, this is set up as most significant bit first, and I have a checkbox here that will change between LSB, or least significant bit first, and MSB, or most significant bit first. And you can see at the bottom here, this timing diagram shows us that updating as we make those changes. The bit clock here, this is configured so that when the MSB starts, or in fact when any of the individual bits start, we are actually on a falling edge of the bit clock. In other words, the clock is inverted. So if I go to my bit clock here, you'll see that I have checked that option there, and we can see the timing diagram update again. Likewise, the word clock, or the LR clock, this is inverted, and it's actually 1 bit clock cycle early in terms of its relative position to the start of the digital audio word. So I have selected the invert and the early option here. And having done this, all I need to do is turn the unit on, and we are ready to make a measurement. So if I now go to page 3 here, we can see that we have a live FFT trace, and we have a green scope trace. And once again, I'm using my continuous time detector to make a THD plus noise measurement. Just to explain in a bit more detail, the continuous time detector is a software configurable series of filters followed by a voltmeter. So this is analogous to our classic distortion analyzer, albeit there is a great deal more functionality because it's controlled by software. And this is one of the analysis instruments in the Dscope package, and there are several more. So I can do things like select a bandpass filter function, or I can measure gain, intermodulation, distortion, noise, etc, etc. And right now I'm measuring THD plus noise, and I'm reading about minus 94 dB, which is exactly what we would expect to see for a high quality 16-bit D2A converter. This is basically performing at the theoretical limits of a 16-bit digital audio channel. Now, what would you do next, having set up a signal and routed it through your D2A converter? Well, there will be many tests that you may want to perform, and at this point you would probably refer to the manufacturer's datasheet to ensure that you're attaining the datasheet quoted specification. And I'm just going to quickly switch to an example of that. So what I have done is, in this test file, I have loaded the manufacturer's quoted response for the amplitude linearity. So on the x-axis of this graph here, we can see the generator amplitude in units of dB relative to full scale, dBFS. And on the y-axis, we have the output from the D to A converter. And we can see that it is linear over most of its range down to close to minus 120 dB relative to full scale, and then we start to approach the noise floor of the converter. So in order to recreate that test, I have set up a sweep in the Dscope software here. And in this example, because I'm going to be measuring a signal that will be approaching the noise floor down towards the lower end of that curve that we just saw, I'm using a bandpass filter response, which will restrict my analysis to a very narrow 1/24th octave band centered around the frequency that is configured in our signal generator. And that will enable me to measure this signal down to very low levels in the presence of noise and get a reliable result. In my source setup here, I need to vary the generator amplitude, and I could simply choose the generator amplitude as a variable here in my source. And if I just change these units, I have options for the start and stop frequency, the number of steps, and whether I choose a regular linear or logarithmic interval between data points in my sweep. Now that may or may not be sufficient for your needs, and I would argue that in the case of this particular measurement where we're looking at amplitude linearity, at this high amplitude end of the measurement here, the signal is going to be relatively stable, and we expect to see a very linear response in the device that we're testing. Obviously at the lower end, down towards the 120 to 140 dB below full scale end of this graph, we might need a bit more resolution in our measurement down here to accurately reproduce this measurement. So what I'm doing in my measurement here, rather than using a fixed linear or logarithmic interval between sweep steps, I'm using what we call a data table, and that allows me to customize the distribution of points between each step. So if I just load that table so you can see it, you can see that my first step is a 30 dB step between the first two data points, as is the next step. Then I go to 20 dB for the next 2 or 3 steps, and then I move to 5 dB steps for the last few data points. So if I now return to my measurement page, you can see that I've copied and pasted this manufacturer's graph such that it's scaled to the same size as my Dscope trace window, just so that I can clearly see whether these two results match one another. So let's hit the Start Sweep button here, and this sweep will now execute, and you will see the effect of the finer resolution at low amplitude. And you can see that we've got a pretty close agreement with the manufacturer's datasheet. So you would now go through your remaining measurements on your datasheet and make the rest of the measurements to ensure you've attained the target response. As I say, we could talk a lot more about converters, but I'm going to go back to my Bluetooth-specific webinar content here and move on to the next subject that's relevant to this particular area. And we're going to talk about some signal processing analysis methodologies now. In particular, I'm going to look at the EQ of the system that we're analysing, the equalisation or frequency response. So just to describe the setup here, I am again using my Dscope Series 3 system, and I will now be reverting back to communicating with the USB dongle device, the development boards that we used in one of the previous examples. It'll be transmitting via Bluetooth, and we'll analyse the outputs from the receiving end of this signal path. Again, what I'd just like to do quickly, if I may, is ask you a little bit about how you would go about making a frequency response measurement, or perhaps how you've done this in the past, or if you've never done this before, the methodologies that you may be familiar with. So once again, I'm going to just run a survey. So that survey should now appear on your screen. As I say, apart from if you're a Mac user, for which we apologise, you are now going to be prompted with a series of options for you to give us the feedback that I'm asking for in terms of the analysis methodologies you're familiar with using, or that you are familiar with in a more general sense, for making frequency response measurements. So as I'm talking, I'm hoping that you're checking all of the boxes that apply all of the methodologies you may have used or may be familiar with. And I will leave that running for a few more seconds to give you an opportunity to make sure you've checked every box that you want to check if you do decide you want to participate in the survey. And I'm going to bring that to a conclusion in a few seconds, so I'll just give you a last chance to hurry along. All right, I will stop the survey now. And let's take a quick look at those results. So it looks like some of you have used signals like pink noise and white noise to make your response measurements. Some of you are familiar with the sinusoidal sweep methodology. Good to see a number of you have used impulse responses. We'll be returning to that towards the end of this presentation. And a good number of you have used multitones as well. That's quite encouraging. One of you has not used any of the above, so what I'm going to do is illustrate to you all the most powerful way of analysing frequency response. And sadly, we don't have time to talk about the pros and cons of all of the above, but I'm going to show you one of the ones that I find most interesting. So let's just close this here and move back to the presentation. So I'll go now straight to my Dscope software again and load a new configuration file. And what I'm going to do actually is use a special case of the multitone methodology that we just saw in our survey there. And I've added another component in my signal path here, which is an external effects unit that I can use to dial in some EQ settings. And the reason for that will become apparent very shortly. Before we do that, let's take a look at what we're actually doing here. So in my signal generator, on this page of my configuration file here, I have a number of options available to me, which I won't go through in detail, but I have chosen the bin center stimulus. And this is a very special type of multitone. We support quite a, well, in fact, a potentially endless range of multitones in Dscope, but this one is a particularly special type of multitone. It is as densely packed as a multitone can be. And what we're actually doing here is populating every single bin frequency in our FFT that we'll use for analysis with a tone component. So in other words, there are 8,000 in shorthand, or 8,192 tone components within this multitone, of which half will occur in the real frequency axis, in other words from DC to the Nyquist limit. So this is a really densely packed multitone. There will be over 4,000 tones in the range over which we will be seeing our analysis. What I have done is I have configured an FFT here in my FFT parameters with exactly the same size, exactly the same number of points, 8,192. And what this allows me to do is to use a rectangular window function, which will impart no spectral smearing on the signal, provided we can ensure a synchronous analysis condition. And having done this, I can then use my FFT measurement, which is a relatively fast measurement compared to, for example, averaged noise measurements or a sinusoidal sweep. This is a very fast measurement in comparison, and allows us to measure all of our tone components at the same time by plotting an FFT and, in simple terms, joining the dots to give us a frequency response. So let's look at that. Well, I have previously made a measurement using a very large FFT size. This is the white trace that you see highlighted currently, and you can see these individual tone components that are the constituent parts of the multitone, the bin centers multitone that I just introduced you to. And once again, if I turn up the monitor volume control on my Dscope hardware, we can actually have a listen to that. Hopefully you heard that. It's a broadband stimulus that sounds very much like noise, and the more tones we have in there, the more noise-like the signal starts to appear. You will notice that the spacing of these tones appears to compress or to get closer, I should say, to avoid any ambiguity there, as we go upwards in frequency. That is just an illusion of the fact that we are using a logarithmic x-axis here, and in fact these tones are equally spaced on a linear scale. So I'll turn this previously measured result off, and I'm going to turn on my live FFT trace, which is now running at the same FFT size as the number of points in my generator sequence. And now we see that we have a very nice clean frequency response. So this is far less noisy than you would see if you were using a pink noise or a white noise stimulus to analyse the frequency response of the system. And it's updating very quickly. And just to give you an indication of that, what I'm going to do is dial in some EQ on my external EQ box that I just told you about a minute ago, and the reason for doing this now will become apparent. I can now dial in individual changes in the EQ settings that allow us to see very quickly updates to this frequency response. So this is happening live on my desk as I'm sitting here. We can see that we're obtaining a very large number of different frequency response measurements in a very short space of time. So if we have a large number of DSP settings that our Bluetooth headset can potentially support, whether that's user adjustable or whether that's controlled within the firmware, it doesn't matter. We can adjust these different parameters and make measurements very quickly, and this is a really powerful way of measuring frequency response, and this is really why I wanted to concentrate on this particular methodology for accomplishing this measurement. Alright, so hopefully that all made sense. I'm going to move on to the next topic now, which is power amplifiers. And once again, I will describe to you my test setup on my desk here, which is starting to look quite familiar. We have our D-Scope hardware and software. We have a USB dongle connected to my PC, which is transmitting audio over Bluetooth to my receiver board. And I'm taking the headphone outputs from this board, but I'm being careful here to use a purely resistive termination impedance at the output of my headphone amplifier, so that I can ensure that I'm driving current into a known load, and I can then use that known load to calculate the power delivered into the load. And 32 ohms is a standard load resistance that we often use for making headphone measurements, because they are typically designed to operate with that kind of a load. Right, so let's switch over to my D-Scope software again. I'll load this test configuration, and whilst that's loading I will just change the connections on my system here. So I've now connected the output of my Bluetooth receiver to the D-Scope input, and let's assign my USB dongle as my output device again. Verify that I've got some signal. Alright, so what I want to do is to find the point at which my power amplifier can deliver no more useful output power. In other words, the onset of clipping distortion, where the output voltage of the amplifier starts to clamp to the supply voltage rails, and we simply can't generate any more useful output amplitude swing. Now I could do this by, for example, I could set up a slider here, and I could move around the signal amplitude, and we can observe on this trace here. This is the green trace is the live time domain trace. The blue trace is the residual THD plus noise, and we can also analyse this THD plus noise figure here, and we can try and manually look for the point where we hit 1% THD plus noise, which is typically used as the definition of the onset of clipping. Now that's perfectly valid, but it's potentially a slightly time-consuming process, because when the amplifier approaches clipping, suddenly the distortion rapidly increases. So it's quite tricky finding that the exact point of that onset. So what I'm going to do instead is use what we call a regulation routine, and this will automatically hunt out whatever our target value of whatever measurement that we want to look for. So this time I'm going to set up the continuous time detector as my my result that I want to regulate to, and I'm going to seek out a target of 1% THD plus noise, i.e. the onset of clipping distortion. And in order to set that up, I need to tell D-Scope what I want to vary in looking for that clipping point, and I'm going to vary the generator amplitude. So when I hit this regulate button, we should see this trace updating here. I'll turn the volume up on my monitor so you can hear this real time as it executes. So off we go. You can see the distortion and the signal level going up and down as we seek to regulate this result, and it has now completed. You'll see here we have a notification saying regulation successful. We can see the residual waveform, the distortion plus noise here in the live scope trace, and we can see that the THD plus noise has hit our 1% target. And that happened at an amplitude of just over 200 millivolts, which is about 1.5 milliwatts in this case. Now there are some additional precautions that you may want to take at this stage to ensure that your headset device is not exceeding the agreed safe limits of output level that may potentially give rise to hearing damage if you were to exceed them. And there is legislation, or at least there are standards that relate to this type of measurement, and in certain countries that is defined in legislation. We actually covered that in detail in a previous Prism Sound webinar, so if you're interested in looking into that, I would encourage you to download or view on demand our previous webinar on the subject of output loudness levels from portable audio devices. But I'm not going to dwell on that today. It's just something you should be aware of if you're designing these products, that there may be potential issues with output levels that you need to be careful with if you want to avoid potential lawsuits and hearing damage to your customers. So moving back to my slideshow here, I'm going to go through the last practical demonstration now, and this is going to involve taking a look at the electroacoustic components of the Bluetooth headset system. And just to explain a typical setup for this kind of measurement, we would use something like a Grass head and torso simulator. Grass are a Danish manufacturer of electroacoustic test fixtures and microphones, artificial ears, all these kind of components and systems that you need in order to verify the performance of these real-world devices as mounted on a real-world fixture that corresponds closely to the kind of fixture that it would be attached to if you were attaching it to a human rather than a test instrument. So I'm going to take the analog output from my D-scope hardware, and I'm going to apply this to the terminals of the headphone amplifier. I've actually probed the headset here. I've broken open the CSR reference design hardware, and I've actually attached some terminals to the I've attached some probes to the terminals of the amplifier. Again, the reason for doing so in this case is because I'm interested in analysing the performance of just the electroacoustic components, and I want to isolate them from anything else that might be upstream, including potentially equalisation, as we saw in the previous example, and I just want to look at the electroacoustic performance. So I'm taking the output from the microphone power supply and connecting that to the input of the D-scope hardware. Now, let's just take a look at why we would need to use a head and torso simulator. And I've alluded to that as I was talking through the previous slide. But just to confirm, the Grass head and torso simulator comprises what we call a Type 3.3 ear, or 3.3 ear. And that has realistic pinna that have representative dimensions and material properties to closely mimic those of the average human ear. And we also have what we call an IEC 711 coupler attached to each ear, and this is designed to closely mimic the acoustic impedance characteristics of the ear canal within a typical human listener. So in other words, with this type of system, we are closely emulating the electroacoustics, the mechanics of the human auditory system, and this is important if we want to be able to accurately determine the sound pressure level as a function of frequency at the eardrum. Now, the observant ones amongst you may have noticed that in the photograph of my test setup, I wasn't actually using a head and torso simulator at all. I'm actually using an alternative, which is called the ear and cheek simulator. This particular model, again, is from Grass, the Danish manufacturer, and this ear and cheek simulator allows us to make measurements on the loudspeaker components of the headset, in other words the earpiece that is attached to the ear or in the ear or around the ear. And this also incorporates some artificial pinna and a standard IEC 711 coupler, so it also mimics the workings of the human ear. Now, if we wanted to make microphone measurements, and we'll talk about that a little bit later, we would need to use the head and torso simulator complete with mouth simulator. But for the purpose of this measurement, the 43AG ear and cheek simulator suffices for the measurements I'm going to show you today. And you should be able to see in my photograph here that there is the ear and cheek simulator, and the second red outline there that I've just added shows you the power supply unit that can be supplied with that particular ear and cheek simulator. I also have a piston phone here that I've used to make a calibration of the system. So I've used a closely toleranced piston phone reference to set up to calibrate the system prior to making the measurements that I'll show you in just a second. So as I say, this is the final practical demonstration, and this is the first time we're going to look at an electroacoustic measurement. And of course we're going to be using exactly the same test system, and we here at Prism Sound feel that it's very important to be able to offer acoustic and electronic analysis capability in a single instrument, for the reason that it brings you potential savings in terms of investment in hardware, and also gives you potential benefits in terms of your workflow working on a single instrument. So we've been working hard providing electroacoustic solutions for the last 2 or 3 years now, and these are now integrated into the D-Scope system. So let's once again go into my test system here. I'll hit the last practical demonstration for today. Whilst that loads, I'm going to just change over the connections on my test setup, which I will need to do to make a measurement. And which I have now done. So let's hit the test button, and I will make some measurements and talk you through them in a second or two. Okay, so we have a number of traces here to talk about, and the first of which is this trace here that I have labelled as the fundamental. Let's just turn off the others for clarity. So this is the frequency response of the transducer mounted into the Bluetooth headset chassis that you saw in the previous photographs. This is the frequency response as you would receive at the eardrum. So this shows us the fundamental. It has a broad peak in the range 2 to 4 kilohertz, and I'll talk to you in more detail about that in a second or two. In addition to the fundamental, we have the second harmonic distortion response, we have the third harmonic, the fourth harmonic. We can go higher if we want to. I'll introduce you to how we've derived these results in just a second. But I just want to explain the fact that on channel B here we also have an impedance measurement. So this is the electrical impedance of the transducer loaded into its chassis, in other words the Bluetooth headset chassis. How have I done that? Well, I didn't explain this in my test setup actually. I've got a diagram here in my D-Scope configuration file which shows you, this top diagram here, how I have set the system up. So I have a resistor in series, a low value resistor in series with the drive unit in the headset, and this allows me to probe with a second channel of the D-Scope analyzer here a voltage measurement that allows me to derive the impedance curve by measuring across this known load. Alright, so let's just talk a little bit about the theory behind what we are doing here. Now you'll see that this is a relatively fast result to execute. It's an FFT based result, and as we saw earlier, that can be, well, in fact that is significantly faster than using a traditional stepped sweep. So how are we deriving all these curves? Well, what we're doing, let's just open a clean page here, go to my signal generator. We are using what we call a chirp or a swept sine stimulus. So this is a fast swept sine, and it's a sine signal that sweeps at a logarithmic sweep rate. And there's a very particular reason for using a logarithmic sweep rate, which we will just look at in a second. This series of measurements has been derived from an impulse response, and this is the impulse response here, the green trace that I'm currently showing you. Now this is the response of the system to a perfect impulse response. In other words, an infinitely narrow, infinitely high peak or impulse. Now, in a real-world system where we have a power amplifier driving a speaker, a power amplifier doesn't have infinite headroom, and therefore a real-world impulse stimulus actually has very poor very poor signal to noise ratio. There's not much energy contained within a real world impulse, so we have to use an alternative methodology, and that's why I used the log swept sine stimulus in my signal generator. If we use a broadband stimulus like a noise signal, a speech file, a multitone, or this log chirp that I'm using at the moment, we can derive an impulse response without actually having to play an impulse through the system. So this gives us much greater energy in the test stimulus and much more resilience to background noise. So having created this impulse response, I can apply a time domain window which gives me my fundamental response, but also there are some very interesting things that occur towards the end of this buffer, this time domain buffer here. And I've just zoomed all the way out. You can see the fundamental impulse at the left hand edge of the screen. What I'm going to show you now is is very specific to the log swept sine stimulus. And if I zoom in on my y-axis here, we will see that at these data points here marked with crosses, we can see some individual discrete impulses. And these actually correspond to the harmonic impulses. And then these individual impulses are what we use to derive the second harmonic, the third harmonic, the fourth harmonic, and potentially beyond. So they can be derived by virtue of the fact that we've used an impulse response methodology combined with the fact that we're using a log swept sine stimulus in the signal generator. So I want to leave electroacoustic analysis for now. Again, this is another topic we could talk about at great length, and I haven't really gone through any of the calibration routines here. But actually, just one final thing before I do leave this here. I did say I was going to explain to you something about the 2 to 4 kilohertz peak in the frequency response here. So let's just turn off that particular result. I'm going to rerun this test and make a copy of it. So I've just expanded the view of the fundamental trace here, just so you can see this clearly. You see this resonance that really starts at about 1 kilohertz and goes up as high as almost 6 kilohertz. You can see this very clearly. What I'll do now is let's just open it on this page. I'm going to engage a pre-weighting filter that compensates for the internal resonance in the IEC11 coupler. That internal resonance mimics the resonance that we see in a real human ear canal, and we may want to compensate for that in our analysis result. So let's just turn this user weighting on, and let's browse to the correct file, which is the free field compensation weighting filter. So this will correct for the resonance in the IEC 711 coupler, and when I rerun this test, you will see that the red trace, which is the live trace, now has updated and gives us a much flatter frequency response, and you may well want to see a frequency response that closely corresponds to the frequency response of the transducer, rather than also including the ear canal resonance here. So as I say, I will leave electroacoustic analysis there for now, and I'm close to concluding, but what I just want to do is introduce you to a few topics worthy of further consideration that we hope to return to in a future webinar. Now, as you'll be aware, as I've explained, we haven't actually made a microphone direction measurement here today. We focused on the headset earpiece transducer, and as I said, we do need to employ a head and torso simulator with a mouth simulator in order to make the microphone direction measurement. And there are some subtleties associated with making that kind of measurement. For example, we would potentially need to equalize the generator stimulus to compensate for the frequency response of the mouth simulator. Hence, you can see in this diagram there's a reference mic attached to the front of this head and torso simulator here to allow us to make a measurement and then calibrate or correct, equalize for that response. We've looked mainly at A2DP or broadband music profiles in our measurements today, and of course in the hands-free profile we're mainly going to be concerned with speech band signals. And there's often quite a lot of heavy signal processing in our hands-free profile or speech profile setups, and that potentially needs some careful attention. A lot of the advanced signal processing algorithms in a typical telephony headset today may not allow a sinusoidal stimulus to pass through the system. So we need to use something potentially broader band and more speech-like. In fact, multitones can potentially pass through some systems, but not all of them. So the IEEE 269 standard for telephony dictates that speech signals need to be used, and some other formats or some other standards specify speech-like signals. So we haven't dwelled on that in too much detail, but as we saw earlier, we can load arbitrary waveforms into the D-scope signal generator, so we can cater for speech as a potential stimulus in the signal generator. I talked briefly about the fact that maximum output levels in portable audio devices, in particular those which incorporate earpieces, headphones, headsets, in-ear buds, all those types of systems, we potentially need to concern ourselves with the maximum output level that those systems can generate from the point of view of hearing protection. And as I said, you can download or view on demand the webinar that we broadcast on this subject a little while ago if you want to look into that in more detail. We haven't talked about automation at all. Again, we've covered that in a little detail on a webinar that we delivered on the subject of multitone testing. Everything that we've seen today can be automated in a production line or QC context, but again, time prevents me from dwelling on that in any more detail. And we also haven't talked about electroacoustic simulation tools. Prism Sound supplies a range of products under the Loudsoft brand, Loudsoft being a Danish supplier of simulation and analysis tools. And we will come back to Loudsoft very shortly. In fact, we have a webinar program looking at electroacoustic design tools, so for designing drive unit motor structures, cone structures, crossovers and enclosures. We'll shortly be publishing the webinar schedule on those particular educational events, so do keep an eye on those individual webinar topics if that may be of interest to you. So for now, for me, I just want to summarise what we have done today before handing over to you for any questions. And in brief, we've looked at a number of areas of functionality of a Bluetooth audio headset or headphone system, and we've taken a few examples to illustrate some of the concepts that we may need to be concerned with if we want to measure this type of system. So we looked at the Bluetooth connection and looked at picking up dropouts or glitches. We looked at board level interfaces and how we can use serial digital audio formats to make direct measurements on A to D or D to A converters. We took a look at signal processing and focused on some frequency response measurements. Then we looked at a brief example of measuring the maximum output power from a power amplifier, before moving on to looking at some headphone or earpiece measurements. And of course, as I said earlier, this is all done from one system and it can be manually or automatically implemented. So I would like to thank you all for your attention. I hope you found today's session useful and interesting. Please do contact us if we can be of any further help. And I hope to see some of you on a future webinar event, so keep an eye out on those webinar pages from us. But from me for now, thank you for your attention and goodbye.